Thank you, thank you. Good morning, ladies and gentlemen. My name is Panagiotis Danoglidis, and today I will present you our latest research about the role of graphene-based nanomaterials for enhancing the CO2 uptake and mineralization in engineered concrete. So, I will start an introduction about the two-dimensional graphene nanomaterials. The two-dimensional graphene nanomaterials in general, and such as the graphene nanoplatelets, exhibit a very high specific surface area, specifically 2 to 3 times higher than the surface area of cementitious grains. So, the high surface area of graphene nanoplatelets and their functionalization with carboxyl and hydroxyl groups play a key role on the surface chemistry within the nanoengineered cementitious systems. And this holds a great potential for increasing the kinetics. The first, a common problem, a common issue in research for all nanomaterials, but specifically for 2D nanomaterials, is how we will control the interfacial properties of the interfaces between the cement hydration products, calcium silicate hydrates, and the layers, the graphene layers. So, I will start the presentation by giving you some details about the graphene nanoplatelets, and in this study we used commercially available graphene nanoplatelets, graphene nanomaterials that come in the form of nanoplatelets. And according to the specification sheets, the nominal thickness of the nanoplatelets is, let me, here, can I use it? Oh. Can I point out, at least with the pointer? Yes. The nominal thickness of the nanoplatelets is 200 nanometers. And here comes the objective of using nanoplatelets. We need actually to increase the surface area that is available in the cementitious matrix to take advantage of the high specific surface area and increase the surface area available in the cementitious matrix. And for this we need to reduce the number of graphene nanoplatelets. So we need to evaluate the number of graphene nanoplatelets, and we evaluated the number of the graphene layers using the Raman spectroscopy. And we found a number of 15 layers of as-received multi-layer stacked GNPs. Indeed, this number falls in the nominal number of layers that are given by the manufacturer, 13 to 16. So we talk about a multi-layer nanomaterial. Now, in our lab, we routinely applied a dispersion method to effectively disperse and exfoliate multidimensional nanomaterials with different dimensions. And in this study, we applied one of this method, and we dispersed and exfoliated the graphene nanoplatelets, so we will reduce the number of graphenes, and this way we increase the available surface area. We monitored the exfoliation, the degree of exfoliation, using again Raman spectroscopy and the same equation here, and we found that after our procedure, we are able to increase the number of layers to 3. So we prepared exfoliated tri-layer graphene nanoplatelets. So it should be noted here that the amount, the volume fraction of graphenes is 0.3 per volume of cementitious matrix, and we selected this volume fraction because this volume fraction actually defines the percolation threshold of graphene nanoplatelets in our matrix. So, in this study, we prepared both cement pastes and mortar reinforced with the exfoliated graphene nanoplatelets, and we evaluated the carbonation processes in these GNP reinforced matrices. So we cured our specimens using a CO2 environmental chamber with 65% relative humidity and 74 degrees Fahrenheit temperature. Now, we quantitatively evaluate the CO2 uptake and mineralization by conducting thermogravimetric analysis based on the ASTM, and this is a standard method to identify and quantify the minerals within the cementitious matrices. And this is a macro-scale investigation, and we also conducted a chemical property mapping at a sub-10 nanometer scale using our NanoIR AFM system to characterize the chemical interactions in the carbonated cementitious systems. So, here. I will start with the results from the TGA tests, and again, the TGA is an ASTM designated method that we can use to determine the CO2 uptake and mineralization by quantifying the weight loss between 525 degrees and 900 degrees Celsius, which is the temperature range for decomposition of calcium carbonates. The higher increase in the weight loss between these two temperatures results in a higher CO2 uptake and mineralization rate. So, we calculated the CO2 uptake and mineralization capacity of carbonated mortars, plain and reinforced with the as-received graphene nanoplatelets, and the results are presented in this slide, and we see only a marginal increase of 8% for the CO2 uptake and mineralization with the addition of the as-received multi-layer GNPs. Now, if we see the results for the carbonated mortars reinforced with the exfoliated GNPs, a much higher increase for the CO2 uptake and mineralization of 26 is observed. And the question that arises actually here is why the use of exfoliated GNPs increases the carbon sequestration potential at a much higher level. Obviously, exfoliation results in a much higher surface area. Therefore, one way of answering the question is to attribute the larger quantity of calcium carbonate observed to the larger surface area available for reactions with the CO2. So we examine the formation of carbonate ions at the nanoscale by conducting chemical mapping using our NanoIR AFM. And here are our results. If we look at a typical, actually, NanoIR spectrum of a non-carbonated, of a moist cure CSH at the 10 nanometer scale, we observe three major peaks. Here, the peak at around 970 wavelength is attributed to the silicon-oxygen bond. And we also have another peak at 1150, which is also attributed to the silicon-oxygen bond. Now, the difference between the two peaks is that the 970 peak is indicative of the so-called silica gel and is expected to be found in every CSH. On the other hand, the 150 peak, the 1150 peak, can be found only in moist cure specimen with a high calcium to silica ratio that haven't been exposed to carbonation. And here we see the third peak at around 1400 wavelength with the carbonate ions is a very weak peak and with a broad range that usually appears due to the specimen exposed in the atmospheric air during the test. Now, In this slide, you see a comparison between the moisture specimen and the carbonated specimen. And notice here how the CO3, the carbonate ion peak, is enhanced. And this shows that the specimen was exposed to a carbonation procedure. And we also identified a second CO3 peak that appears at around 870 wavelength, again due to carbonation. Now, the silicon oxygen peak at 970, as mentioned, is always there. And however, the second peak at 1150 has now disappeared. Remember that the silicon oxide peak at 1150 wavelength appears only in moisture specimens that haven't been exposed to the carbonation, and due to the existence of this peak, the calcium to silica ratio is high. Now, in carbonated specimens, the calcium is consumed due to the formation of the calcium carbonates. Therefore, the calcium to silica ratio decreases and this peak disappears. Now, I will continue with the graphene nanoplatelets. And actually, in this slide, we show the FTIR spectra of suspension of the nanoplatelets with as received and tri-layer. The as received is a purple curve, and the tri-layer is the red curve. And adding graphene nanoplatelets typically modifies the IR at the wavelength range of 1970 to 2200, where the carbon-carbon double bonds can be visible. Now, there is a distinct difference at the exfoliated GNPs, as this material, the tri-layer GNPs, exhibits a strong peak at around 1650 wavelength. And this peak represents the carbon-carbon double bond and carbon-oxygen double bond, and it is attributed to the attachment of carboxyl and hydroxyl groups onto the CNT surface, which is also known as surface functionalization. So now I will show you the spectra of the GNP cementitious materials. As I mentioned before, adding GNPs typically modifies the IR wavelength range of 9070 and 2200, where the double carbon bonds are visible. We are not showing here this peak in this graph because our NanoIR stops at the 1800 wavelength. But in this, the NanoIR of exfoliated GNP cement-based shows a characteristic peak of the exfoliated GNPs at the 1650 wavelength, where the double carbon and carbon-oxygen bond that shows the attachment of carboxyl and hydroxyl groups onto the surface of graphene exists. Furthermore, the carboxyl and hydroxyl groups are active sites that promote the reactions between calcium ions from the calcium silicate hydrates with CO2. So, by looking our NanoIR spectra here, we see that the CO2 3 peaks are intensified, as expected, showing a 60 to 75% higher absorbance intensity, which is indicative of a higher amount of calcium carbonates. Remember here that the silicon oxide peak at the 1150 wavelength appears only in non-carbonated specimens, and this is due to the existence of the high calcium to silica ratio. Now, during carbonation, the calcium is consumed due to the formation of calcium carbonates. Therefore, the calcium to silica ratio decreases and this peak disappears. And furthermore, The characteristic silicon to oxygen peak at the 970 wavelength appears identified here, and please recall that this peak is always present in specimens that contain calcium silicate hydrates, and it does not change in carbonated specimens. However, now the presence of the exfoliated tri-layer GNPs contributed to a higher polymerization degree of the silicates and the formation of longer silicate chains within the system. In this slide, before the conclusions, I would like to show the NanoIR spectra of carbonated cement-based materials with the as-received graphene nanoplatelets, the green curve. First, we see that the silicon-oxygen peak at 970 appears in both exfoliated and unreceived GNP-reinforced carbonated specimens, with the higher peak attributed to the exfoliated specimens. Also, comparing the carbonated specimens that contain the as-received and exfoliated GNPs, we observe that the exfoliated GNPs result in higher characteristic peaks of the carbonate ion, showing the existence of higher amounts of carbonates. Hence, a higher degree of carbonation observed. So, I would like to conclude my presentation with some important remarks. While we can use both multi-layer and tri-layer GNPs to increase the concrete's capacity for CO2 uptake and mineralization, the use of highly exfoliated functionalized GNPs are able to better enhance the CO2 uptake and mineralization due to the formation of higher amounts of calcium carbonates. We saw that the 28-day CO2 cured mortars reinforced with the exfoliated tri-layer GNPs exhibits a much higher CO2, 26% higher CO2 uptake and mineralization. And the use of exfoliated few layers, the tri-layer functionalized GNP, is crucial actually to provide active sites to promote the chemical interactions between the CO2 and the cement hydration products, thus to facilitate the production of calcium carbonates. I acknowledge to our NSF PIRE project, and thank you for your attention.